Welcome to Avian's official systems engineering podcast. This is episode 7, digital engineering. Today I have Vince, Jim, and Rich with me to talk about digital engineering, what it is, where we see it going, how some of our customers are using it, and how we can support them in the future. First of all, Vince, since this is your first time on the podcast, will you please introduce yourself and give a little bit of background about what you do for the company and what you do for your customer?
Sure. My name is Vince Vanoss. I'm the Science and Technology Lead for PMA 209, which is the Aircraft Common Electronics Organization. PMA 209 supports acquisition and integration of ARC 210 radios, common mission computers, precision navigation and timing, air traffic control, CNS ATM functions, as well as a number of cats and dogs related to reaching out to every program office, finding out what their challenges are, and helping to structure an approach with OpNav in order to prioritize which programs get obsolescence upgrades over others as they try to manage the overall naval aviation budget. Been doing that for about 2.5 years. Before that, I spent 6 years with the V-22 program, doing much the same role in science and technology, focused exclusively on that airframe. And prior to that, 20 years as a Navy submarine officer with a stint in naval intelligence, a year in Iraq putting jammers on the backs of Humvees as the Joint Crew Composite 1 Squadron chief engineer. And then the last 6 years were with the Tomahawk program as the submarine integration lead.
So a pretty extensive background and definitely an expert in what you do, like a lot of our, all of our guests that are on this podcast. So glad to have you on this one. Of course, Jim and Rich have been on before, so I'm not going to make you guys introduce yourselves, but let's dive into this topic, digital engineering. And the easiest place to start is, what is it? What is digital engineering? Let's start just with that question. Let's answer the what. So whoever wants to tackle that, go ahead.
So I'll take a shot at it, and I'm sure others will join in to help me get this squared away. In our previous podcasts, we talked about getting into the digital environment and developing a digital representation of the weapon systems we're trying to develop. And MBSE takes one of those first major steps and gets us out of developing weapon systems based on paper specifications into a world of developing it digitally in a model. When we talk about the digital environment writ large, we find ourselves thinking about what's the entire digital environment out in the design space that we have to address. There are elements of work that have been going on for a long time in the areas of flight test, sustainment, production, and so on that have moved to digital environments. The next step for us is to try to stitch those things together into and make all these models work together so that the output of the system model with all the design features can seamlessly lead into a test environment that will allow us to do capability-based testing based on system model outputs that describe the actual functionality of the system. This will allow us to learn more about the behavior of the weapon system sooner, reduce risk, and reduce flight test time, and save a lot of money. From there, we get the opportunity to look at production and sustainment with the integration of the system model outputs into other modeling tools such as CATIA in support of production, and also in support of PLM models that are routinely used today to support aircraft in sustainment, so that we can get to the point of understanding the configuration of not just the general design, but for every BU number out there. So we're trying to move into a broad digital environment that reflects the weapon system we're trying to develop.
there's a huge advantage with digital engineering. One of the advantages, probably the primary advantage, is it becomes the single authoritative source of truth for information and knowledge of that weapon system. So, in the past, where we've had paper specifications and documents on various aspects of the aircraft and the weapon system, we now have that all digitized and linked with complete traceability, and essentially the model and the federation of models across the digital engineering spectrum become the single authoritative source of truth, which really is pays huge dividends.
I think there's, at least from my perspective in science and technology development, we try to think 5 to 10 to even 20 years in advance. An awful lot of times I see the concept of digital engineering split into between two areas. One is purely in the acquisition world, like we're talking about, and a lot of times we haven't had the digital analysis tools, the capabilities in the past. A perfect example, hydraulic actuators on the V-22. There's, I think, 22 or 23 major actuators to do everything from have the nacelles tilt to different control surfaces and major issues. Specifically on the nacelle tilt actuators, the aircraft was designed in the late 80s, early 90s. And so they made assumptions on the number of times that the nacelles would tilt in a flight, the number of number of missions that a particular aircraft would go on, how it was used, and they laid all that out to figure out the net number of cycles that actuator would need. So when they made the design specifications for that actuator, using 1980s, 1990s algorithms, computers, technologies, they said, we are going to design this actuator to these specifications, and we're going to add in a engineering risk factor, of safety factor of however much you wanted to. And then we are going to say, this is going to be a life-limiting component. So we have design, we have MBSE, the actual design of the component, we have product lifecycle management, all wrapped in, and said, at 5,000 flight hours, we are going to replace this actuator. Everybody put a rubber stamp on it, and they sent it on its way. And then with the delays in the V-22 program until it finally got into full rate production and now ending production, you get to a point where everybody is happy-go-lucky and we're going on until you start to get that first couple of aircrafts approaching 5,000 hours. Now, the question is, do I take that actuator out and replace it with another actuator rated for 5,000 hours? Do I spend money now to go in and redesign that actuator and make it good for 10,000 hours? Or do I go back and completely redesign it for something that maybe my models have changed since then, and I need to completely redesign that? Redesign costs money, acquisition costs money, and everybody is trying to make a decision on this one component. And you have a whole host of other life cycle limiting components that are also in need of replacement and redesign. So we've built ourselves into this constant cycle of, what do I do now? Where do I spend my money? If we have good models, or if we need to go back and retrain the engineers who maybe those models were built before they even got here, be able to open up those models, tear them apart, put them back together, and we might even be able to go in and say, we've done a better analysis of that life-limiting component, and we were way, way over conservative. That's not just good until 5,000 hours, that's good until 15,000 hours. Having a decision like that is literally billions of dollars could be saved if we had that as digital engineering. The other part of digital engineering I see as the operational. Being able to take that collection of acquisition-based models and structures and stuff like that and turning it into something that can be used by the pilots. The easiest example of that is we have structural models today of the component skins of various aircraft, the composite materials, how to repair them, how many layers they are, how strong they are. You could take those if you had active measurements at the time and provide that to the pilots in a combat situation to say, oh, by the way, you have taken a number of hits from bullets and now your structure has been degraded by X percent. So you either need to not put so much stress on the airframe or maybe consider moving away from getting shot at. Those are the sorts of decisions you want the pilots to be making, actual combat, as opposed to responding to a bell or a whistle, alert or warning or stuff like that, that is taking their mindset away from fighting as opposed to fixing.
Yeah, so as you're explaining that last scenario, I'm thinking of this video game that I used to play, and it's exactly that, where it's obviously it's a lot easier in a video game than in real life, but as you're getting shot by bullets, you're seeing your airship or your airplane kind of degrade and health is I guess that measurement. But to have that in real life, I mean, you can save lives, but it's going to help the pilots make really great decisions really fast. That comes out of, it sounds like, digital engineering. So when I was doing a little bit of research for this episode, everything that I came across had like this, well, the graphics that I saw had all these different pieces of engineering, I guess, or different disciplines within engineering around the word digital engineering. So in my mind, and you guys can correct me if what I saw was wrong, but in my mind, that means that like we have all these moving pieces, and I think this is what you guys were saying, have all these moving pieces that are happening. You have the systems engineering, you have all the other acquisition stuff that is happening, and digital engineering is kind of like the glue that ties it all together. Is that correct?
So, Ian, I think you're onto something here. Absolutely. So one of the big advantages of going to this, quote, single source of truth, or maybe more accurately, a common source of truth, is to enable collaboration from the thousands of engineers that are supporting and developing the program piece by piece. And in Vince's description of just imagine if we could tailor the design of components so that they were all matched in terms of life, this collaborative ability within model-based systems engineering allows you to do that, so that that's going to become a reality. And then in our expanded conversation here today, the next step is to expand that into the PLM environment, where the people who handle supply chain and logistics, and to ensure parts on shelves and monitor readiness more real time, they're going to be able to do that. So yes, the collaborative feature of everything we're talking about here is extremely important, and frankly, none of this would be worth a damn if we couldn't do that.
Go ahead, Jim. It sounds like, or it looks like you're about to say something.
No, what I was going to say was, there's a big movement within DoD to go to digital engineering, transform to digital engineering. That's a lot of work. There's coming up with standard ways of doing business, comes up with semi-standard tool sets or identified tool sets to be able to do that. Training, workforce culture, a lot of those things. One of the enablers that DoD, that OSD wants, has sort of identified as a way to implement this digital engineering is through pilot projects. So, because there's a lot of the art of the possible when we talk about digital engineering. When you start using computers and you start using models, when you start going into sort of the capabilities of these models and the capabilities of these model interactions, you start coming up with all kinds of different ideas, the art of the possible, on how we can use these to do our jobs better, so to speak. They also they recognize that pilot projects are key enabler to making sure we get a good digital engineering strategy.
Yeah. So, Vince, did you have something to add?
Well, one of I taking notes as people are talking, and one of the things, I am a big proponent of standards. Let's get a government standard, get it open, get everybody on the same page. One of the things I have seen though is 10 years ago, even less than that, everybody was on the DODAF architecture. Everybody had to have OV1s, CV1s, all of that, and there was an arcane science behind whether or not you got DODAF certified. The current wave is SysML, and okay, these are the tools that we're going to use to do that. What I've found is, especially working with some of the people who deal in big data, some of the data pools that NavAir set up for some of the common data calls that are used not only with contracts and with other stuff, is you talk to the data engineers, the data scientists. For years, the data experts at NavAir have been the retired maintenance chiefs, the people who are really good at using Cameo, at using any one of the Alice, any one of a number of the maintenance type systems. The people that are violently in need of and are being recruited not only by NavAir but by Intel and General Electric and people like that are 22, 23-year-old pure data scientists who don't care one bit about where your data comes from or even what your data is. They want to know what the data is structured like, and we've talked to people in terms of a common maintenance system and common data systems. Those sort of people really say, don't tell me what system this comes from. I don't care whether or not it's proprietary or not. At the end of the day, they, by contract, have to give it to the government. So long as if I have 15 minutes to understand the rows and columns, I can scrap together whatever language I'm working in, be it C++ or whatever. I'll make my own scripts, I'll do my own data mining, and I'll come out with a big data analysis. One of the things General Electric is doing, they have hired some people who fit that profile. They are taking data from every single one of their jet engines on every single aircraft, and in some cases they've built models for their competitors. And as a aircraft takes off, goes through a mission, comes back, they download all that data and they have a digital twin of that particular engine, not just type of engine, that particular engine. So engine number 1 on FA-18 Buno number 32. Every time that engine fires up, goes down, whatever happened to it, they do it on that digital twin. And the value of that is they have a digital twin for every engine out there in the fleet. So if engine number 64 runs into a problem, they can compare their digital engine 64 with all the other engines across the fleet and see whether or not it's a systemic problem or if it's just to that engine or that engine with particular model or whatever. So those are the big data concepts. And if we focus too much on coming up with a standard program or a standard, okay, everybody's going to use Excel until somebody comes up with something else, we're still going to be behind the times. And those people who maybe don't come with their own pre-assumptions and training, if we start taking a look at the young, hungry data scientists, those are going to be the people that solve our maintenance problems, our design problems, and everything else.
Yeah, I think that just proves the point that we always hear, that the knowledge is in data, or the data is knowledge. So Before we started recording, Rich, you were talking about a recent demonstration, Moxie. Is that something that Navarre was working on, or can you just expand on that?
Yeah, sure. And Moxie was just a model attempt that took the output of the system model performance that was predicted by the MBSE model and allowed them to go and do a modeled test run of the performance of that aircraft given the output of the system model. This is all digital. It's all it's not real flight test. It's the modeled flight test. And what that enables you to do is take those results and based on what you get, allows you to focus more on capability-based results that allow us to figure out, is this thing going to perform? Are we really validating that the weapon system we're building is the right weapon system in advance, and to do it much earlier so that we reduce risk, and it's typically brought on in flight test because we actually get real flight tests late in the program. This allows you to do that a lot earlier and do multiple iterations.
Sure.
I'd also like to pick up a little bit on what Vince said, because what he brought forward here was really interesting in terms of not getting tied down into specific tools. I think all of us are still waiting for ADA to become a thing. I don't think that's going to happen. A lot of what we're talking about with the digital environment is really agnostic to tools. The tools will come and go. But what we're really aiming for is to find a way to do systems engineering faster and more effectively. I did some interesting work and looking into what SpaceX has done and the way that they've gone and evolved their concepts for flight travel iteratively. Yeah, and what they did was they were able to go and design, build, test, iterate, redesign, rebuild, and do it and go through a design process that was much faster and resulted in a real capability to get into space faster with better design. So they took a little bit different approach where they said, well, we're going to control everything. We're going to build a concept. We're going to go fly it. We're going to go turn it around. We're going to make adjustments as we go and get a much better design. So they have their Falcon rockets. They went from Falcon 1 through Falcon 9, which is today's capability. And they did all that over a period of 4 years, which is amazing. That was enabled by the ability to model results and know where you're going to end up with each step. This kind of forward thinking in terms of systems engineering is where we're trying to go. And can we take the defense environment and do that? Time will tell. Our acquisition system may not allow for all of that, but there's a lot that we can do to streamline the process and get to better answers faster.
Yeah, definitely. And I think mentioning SpaceX is obviously always a cool thing to do. But I think you're exactly right that they, and maybe it's just the fact that they don't have the same restraints as working directly for the government. But it's incredible how quickly they were able to go from 1 to 9, and like you said, 9 is their current iteration. And I'm sure they're still running tests and putting it through models and all kinds of stuff with that to figure out how to make it better and how to make it faster, I guess.
Well, one of the things along those lines, when I was with previous program, there was some discussions about new maintenance approaches. Specifically, V-22. Every time they took off a windscreen, the seal that held the windscreen in place would get corroded over time, and they got to a point where they really didn't want to take off the windscreen unless they really had to, because with maintenance, you open something up, hey, there's corrosion, now this aircraft is going to be down longer. The science and technology people over at NOC AD had really leaned forward, and they'd come up with a new technology for a plasma flame spray of adding metal particles. So the idea was, hey, we have this area where It's real difficult to do traditional weld buildups rather than pulling apart the frame and putting a new one on there, and how long that would take, and depot level repairs. What they could do is brush all the corrosion off, get it down to as much bare metal as they could, and then they would put this flame spray over the top, and they would build up that structurally and get the repair done. And I remember sitting in a room with probably about 30 different people. You had the science and technology people who had funded the development of this new technology. You had the current platform engineers who were structural engineers who were mostly platform focused, V22, some other rotorcraft platforms, FA-18. And then you had the legacy, the knock engineers who had been there, the quote unquote graybeards, the ones who had been there for 20, 30 years. And the discussion centered around, okay, this looks like some really good technology, and this looks really interesting, and we really like it, and we see all your models. Way back when we built platform whatever, in order to qualify a stick weld buildup or something else like that, we had to go and physically take this structure and put it through 5,000 cycles and prove that after a certain amount of time it still would work. And we have to do these physical tests. And even though you have literally given me terabytes of modeling data, there is no way for me to take that model and compare it to what I saw with my own two eyes and what I'm willing to sign off on. So that legacy of that cadre of old guard, so to speak, that I think is really a opportunity where if we can figure out either tools or training or opportunities to educate those people and help them understand that even though you did a test X and we are providing tons more data but not in the same format, we will help you get to a point where you can believe this and lean forward and adopt these new qualifications, because the people who handle qualifications of testing, not just test design, but the ones who actually, the warrant holders who actually have to sign off, and quite frankly, they're extremely fond of saying is, because if I sign off, somebody could die, I'm not ready to push the I believe button. That's the group that I think.
So I think this is a good segue to start talking about two things: where you guys see digital engineering going and the digital environment going, and also along that path, how you see Avian supporting where it's going in the future. So along the lines of what Vince is saying, educating folks that may not have the knowledge that they need. What other types of support could we provide customers that are moving more towards this digital environment?
Well, what I was going to say is, Vince brought up a number of cases where I think if we get to a digital engineering and sort of that common source of truth, if you will, across models, across data, across knowledge, decisions can be made a lot faster. They can be much better informed decisions. So when we put a new repair concept or looking at changing life limits, you're better prepared to understand what that may mean to things like your cost, because your elements that make up cost estimates will be more accurate. You'll have situations where you'll understand your life predictions based on the physics of the models and things like that. So that's one of the many advantages of digital. What I see as digital engineering.
Rich, did you want to? We lost you right when you started talking. So did you want to jump in again?
Yeah. So you were asking the question of where are we going as a company, and I mentioned that we've been supporting the system engineering team at NavAir with their transition to model-based system engineering, and we've been helping a lot in development of process and policy and doing actual model development with them. Furthermore, we're providing a lot of support with programs directly. And we have the opportunity to help them build individual models for their programs. I'm sure Jim could talk a lot about some of the advanced work he's doing on his new program. I'm engaged in a new program that's getting ready to take off, and we're starting from the very beginning to figure out what's the best way to design and develop a program office that will live in this digital environment and support a digital environment. With that comes the opportunity to help them understand what the art of the possible is. And at Avian, we're looking for ways to demonstrate new capabilities that are coming forward. Jim mentioned the idea of doing demo programs. There are already some demo programs that the SET team has done and that we've been participating in. There's one called Skyzer, which is taking deep dives into model-based system engineering. We're looking at the opportunity to develop broader models that will allow the integration of a model-based system model that comes out of Skyzer and attach it to some of these other emerging technologies that we're seeing with PLM and that we were talking about earlier with Moxie and flight test, so that we can bring the whole process together. And we are learning to integrate the needs of systems engineering, which this is really all about, program management, as well as the ability to just model stuff. And we're bringing that together and helping programs move forward.
I think two things come to mind when we talk about what Avian can do. On one hand, we're leaning forward in looking at new ways to communicate, not just in terms of person to person, but component to component. Because once we understand that, once we understand the data, there's an awful lot of what we look at in terms of aircraft and why we do things, that it's been an awful long time between the last time somebody asks, well, why do we do that? It's because we've always done that. Electrical distributions. You have generators that have to be attached to a drive shaft or to an engine, typically in a nacelle or out on a wing. And those generators produce energy, goes into the fuselage, into a circuit breaker box with a number of circuit breakers, and then the power for that breaker goes back out of the fuselage, out into the wings to power something literally 3 feet away from that generator. The ensuing wiring going back and forth multiplied over several hundred different loads adds literally hundreds, if not up to 1,000 pounds worth of copper wire. And every time you have something moving, an opportunity for that wire to become chafed or broken or stuff like that. So if there's ways that we could, and the only reason we have that design is shortly after the Wright brothers flew in Kitty Hawk and somebody wanted to put something electrically powered on an airplane, we reverted back to what we knew at the time, wiring system of a house. You have power input and you have a breaker box. We've trained our pilots to, hey, in times of emergency, you need to shed loads and flip breakers. And do you want your pilots paying attention to that or paying attention to who's shooting at you? So if there are ways that we could take those decisions away or make them easier or managed by AI, if we can come up with architectures for electrical distribution or any one of the other systems that if we start from a clean whiteboard and redesign today, maybe not to immediately put into an existing aircraft, but at least understand it to the point where we can start investing today in those future decisions so that when we do get to redesign, we already have the technology and it's not just something that still remains 10 to 20 years off. The other thing is, I'm not sure if Chris Vincent has been on some of these discussions, but he did some work for the trainer program, and I also brought him in for V22. We were going through some massive redesigns and rework of the nacelles. Any typical for me, as being a submariner, you have teams of people that sit there and figure out all the maintenance changes to the ship. So you go into the shipyard, they fix everything at once, and then you go back out to sea. I was disoriented when I first got to V-22 because you're going through a production line and people will cut in a change on aircraft 200. And then they'll use aircraft 200 design to figure out a change to aircraft 210. Just so happens if they don't get a chance to get all the changes to aircraft 200 done before 210, when they fund 210, they're ready to go. Now you have to spend more money to figure out what other changes need to be made because they didn't get to that previous change. And so literally a couple of years ago, V-22 had upwards of 80 different configurations on their one common MV-22 Charlie. So they've been working diligently to try to neck that down to a common configuration. What Chris was able to do was take all of the previous maintenance data for every aircraft and then put it into a model that basically said, all right, based on where this aircraft was or what it was doing, first thing we're going to do, I have the stack of about 30 different changes we want to make to an aircraft. Let's organize them by area, by type, so that instead of going in making one change, so long as we have this panel pulled out, let's make all of the changes in this panel at the same time. And secondly, being able to take how the aircraft was flown, maybe by where it was flown, by what squadron, maybe by place. What we've found out is aircraft in Hawaii are flown different than Cherry Point. So being able to take those and then on a squadron by squadron basis, help the fleet figure out which aircraft they want to put through the change pipeline first. Is it your hangar queen that you've been using for parts and just sits there? Is it, if we're going to group things together, is there a smarter way to take one of your combat ready aircraft and only take it down for 3 months in order to make a bunch of changes? Or do you do one change and send it right back out there? The beauty is once you have that data, you can come up with different profiles and play what if and maximize anything. If you want to maximize the number of fleet ready aircraft, you can do that. If you want to maximize the number of changes made, you're lengthening the overhaul period, but you're also bringing things out closer to a common configuration. Once you have that data, you can play what if all day long and help the fleet, help leadership, and everybody else.
So that's actually a great segue into the next
the
episode, which Chris will actually be on. Spoilers, we record these ahead of time, and we actually have recorded that episode, and it's exactly what Vince is talking about. So if you're interested in learning about, from Chris himself, what Vince is talking about, definitely be on the lookout for that final episode in this first run of podcasts. I think this is a good place to wrap up. Is there any last minute thoughts that you guys want to throw in about digital engineering?
No, I think in summary, perhaps the best thing to say is that we're leveraging all the work that's been done in many areas of digital engineering and digital environment and trying to bring them together as a next step. And I don't think we're far off in terms of some number of years from seeing a fully integrated digital environment that's computer-based and that all the parties of a development team are able to collaborate on together and have that true single source of information for everyone. I know I wish I had in my days of systems engineering the ability to not waste thousands of man hours just chasing down which version of the spec am I looking at, and does everybody have the same one? That's all gone now with the where we're going with model-based, and we'll be able to expand that to the rest of the development process and bring stuff out to the fleet faster, meet the overarching desire of the command to have capability faster, and enhance readiness in some of the ways that Vince is talking about. Over.
Yeah, and I think that everything that you guys have been saying drives those points home that we talk about almost every episode, where everything that we are doing to help our customers reduces risks, it saves money, it empowers them with the knowledge that they need through the data, and really everything that you guys said this episode showcases all of that. So great job there. If there's no other last minute thoughts, we'll wrap it up here. Rich, Jim, Vince, thank you for joining me, and I will see everybody next time. The Model Vision podcast is brought to you by Avian. At Avian, we provide extraordinary support in the areas of model-based systems engineering. We help our customers detect problems early using modeling with a purpose. With Avian's MBSE network, we provide a collaborative ecosystem to access, define, and implement a tailored MBSE approach for program success. Avian's model-based systems engineers work with SysMill using Cameo software to replace the document-centric nature of typical systems engineering. Our engineers expose vulnerabilities within your system before implementation, ensure speed to the fleet with a solution that brings clarity early, enhances the chief engineer's capabilities, creates a holistic view allowing for better decision-making, and simplifies complexity. Everything works together to bring certainty to your design. If you're interested in learning more about Avian's capabilities within MBSE, you can visit avian.com/capabilities.